When we look at a chemical formula, usually the ratio of elements in that formula is already in its simplest form, its most reduced form. However, with some organic molecules, and sometimes when we have ionic compounds that involve the peroxide ion, those subscripts may not be in the simplest ratio. And so when it comes to characterizing a compound based on the ratio of one element to another, for instance, hydrogen peroxide, H2O2, the hydrogen and oxygen are in a 1-to-1 ratio. However, the formula is H2O2. So the actual ratio differs from the simplest ratio. And this is where the difference between empirical formulas and molecular formulas come in. Empirical formulas refer to the simplest whole number ratio of elements in a compound, whereas a molecular formula illustrates the actual ratio. So in the case of hydrogen peroxide's simplest ratio is 1-to-1, therefore its empirical formula would be HO, whereas the molecular formula, the actual ratio, is 2 hydrogens to 2 oxygens, and therefore the formula would be H2O2. So we need to be able to distinguish between the two of those, but we also need to be able to calculate from given recorded data what the empirical formula and the molecular formulas are for any given compound. Starting with empirical formulas, there are 2 ways that we can determine the empirical formula. Both pretty much follow the same solving scheme. They just start with different known amounts. So the first type that we're going to talk about are how to determine empirical formulas when you are given the masses of the elements that are present. And this might be true if you ran an analysis on a sample, instrumental analysis, and the results you got were literally a mass, so many grams of this element, so many grams of that element. You can use that to determine the simplest ratio. The first thing that you need to do in this process is to use the molar mass for each element present and convert that mass in grams into moles. Once you have converted every single element's starting mass into moles of that element, then you need to compare those mole numbers and choose the smallest one. Whichever number is the smallest mole number, you divide all of the mole numbers by that smallest value. And the quotients that you get from that division will serve as the subscripts in the empirical formula. If we take a look at this example, what is the empirical formula for a compound if 2.50 gram sample contains 0.900 grams of calcium and 1.60 grams of chlorine? So we see that the 2 elements that we have in the formula will be calcium and chlorine, and we start with the mass of each one of these. Now I've placed each of these values over 1 just to help keep straight how the cancellation of the units will occur. You are not required to put these values over 1, but it can help to simplify things. Using the molar mass for each of these elements, to 3 sig figs taken from the periodic table, we see that the grams of each element will cancel out, leaving us with moles of each respective element. And solving for the moles, we see that we get 0.0224 moles of calcium and 0.0451 moles of chlorine. The next step is to compare the mole numbers and choose the smaller one. In this case, that would be the 0.0224. So we divide both mole values by 0.0224 moles. And we see that the moles cancel out, so again we are getting a unitless value, and these numbers that we will get as quotients will serve as our subscripts. And calcium obviously will come out to be a 1. Chlorine comes out with the values that we have and the number of significant digits, comes out to be 2.01. A basic rule with these empirical formula calculations, when you do this step where you divide by the smaller mole numbers, more times than not you will get whole numbers. There are some exceptions where you get a decimal value that's equivalent to a fraction. We'll take a look at examples of those. But by and large, the majority of the time, those quotients should come out pretty close to whole numbers. Here you can see that to 3 sig figs it comes out to 2.01. As long as you are extremely close to the whole number, and by extremely close I mean you're off by hundredths or thousandths if your sig figs go out that far, then you're okay. So 2.01 is close enough that we could round that off to 2. If we got 2.1, that would be a bit far for rounding purposes, at least for a problem that is we are presented with the information here. Obviously, when you are running an experiment in the lab yourself, if you are not as experienced running the experiment, obviously you're going to allow a larger margin of error, at least until you gain that experience. But for the most part, the values should come out to be whole numbers. And so the 1 and the 2 thus become our subscripts. We don't show a 1 as a subscript for calcium, but the 2 we show as a subscript for chlorine. So our empirical formula, the simplest formula, is CaCl2. Sometimes the empirical formulas are the same as the molecular formulas, other times not. I alluded to the fact that though most times when we divide by the smaller mole number we get a whole number, there are times where we will get a fraction or a decimal value that is equivalent to a fraction. However, those decimal values should be equivalent to a fraction like 1/4, 1/3, 2/3, 1/2, something that we can very easily correct for. So if your division of the smallest mole number gives you a 0.5 or a 0.25 or a 0.33, even a 0.67, all of those decimal values are equivalent to a common fraction, 1/2, 1/4, 1/3, 2/3. So what you need to do is multiply that mole number as well as all the other mole numbers for the different elements by a common factor, so that what you end up with are whole numbers for each and every element. So for 1/2, if you had a value that ended in 0.5, you would multiply by 2. If it ended in 0.25, which is 1/4, you'd multiply each value by 4. 0.33, 1/3, or 0.67, 2/3, both of those have the common denominator of 3, so you would multiply those values by 3 to clear the fraction out and leave you with whole numbers. What is the empirical formula of a compound that has 7.22 grams of nickel, 2.53 grams of phosphorus, and 5.25 grams of oxygen? Starting the problem as we did the previous example, we begin with the number of grams for each element and use each element's molar mass to convert it to moles. Examining those mole numbers shows us that 0.0816 moles is in fact the smallest mole number. A point of caution here, make sure that you pay attention to decimal places and not just the digits themselves. Because of the placement, the decimal place that the 8 occupies, phosphorus's mole number is in fact the smallest of the 3. When we divide these mole numbers, we find that for nickel, we actually end up with about 1.5. Phosphorus comes out to 1, and oxygen is close enough to 4 that we can round it off to that whole number. But that 1.5 for nickel is going to be problematic. So what we need to do to clear out that half, we need to multiply it by 2 to make it a 3, therefore a whole number. But whatever we do to nickel, we also have to do to phosphorus and oxygen. So multiplying all of those quotients by 2 gives us the values 3, 2, and 8 respectively for nickel, phosphorus, and oxygen. And these values then will become the subscripts in our empirical formula. And we get Ni3P2O8. Now a side note, in looking at that formula, you may wonder, well, what compound would this form? Because knowing what we know about ionic compounds, the first element is nickel, so that would be the cation. Everything following that would be the anion, and we don't know any anions, or haven't discussed any, with the formula P2O8, but if you remember that everything following that first element should be the anion, you've got phosphorus, you've got oxygen. If you look at those two subscripts, they can be reduced to 1 and 4, PO4, which is phosphate. So for what we're looking at right here, getting the empirical formula, this form, Ni3P2O8, is fine. If you recognize that, oh, that's supposed to be phosphate and it's 2 phosphates to 3 nickels, you could rewrite the formula Ni3 parentheses PO4 parentheses 2, and that would be acceptable. Sometimes an instrumental analysis of a sample will give us not an absolute measurement of how much of each element is present, but rather a relative amount of how much element is present. And this relative amount is usually given in the form of percentages. So solving for an empirical formula starting with percentages of each element present is really no different than what we've discussed in the previous 2 examples, with one small but very important addition to the process at the very beginning. And it's almost like geometry class when you are writing a proof, how you have to specifically and explicitly state every assumption you are making so that you can validate the steps that you are taking in that proof. Same sort of idea here. The idea is, if we are starting from percentages, we know that we need to start our calculation with a mass in grams. Well, the simplest way, and the way to get to that point with the least amount of extra calculations and conversions and things of that nature, is simply assume that the sample that you have, assume you have 100 grams of it. That way, your percentage just turns right into the grams. For instance, if you had 55% carbon in your sample, what the analysis gave you, then if you assume that the total mass of that unknown sample that the 55% was measured from was 100 grams, 55% of 100 grams is simply 55 grams. So by making this one very small, seemingly insignificant statement of assumed total mass is 100 grams, you are literally opening up the door for yourself to legitimately be able to start the calculation with a certain number of grams, whatever it happens to be in the given problem. So you physically need to write this statement at the beginning of your solution, and then the process is exactly the same as we've discussed. Convert each mass to moles with its molar mass, compare the mole numbers and divide by the smallest mole number, and the quotients then become the subscripts. If the quotients come out to be a fraction, as in the last example, then you need to make the correction as we discussed previously. In this example, we have a compound that has a percentage composition of 40% carbon, 6.71% hydrogen, and 53.3% oxygen. And the question posed to us is, what is the empirical formula? The very first thing we do, seeing that we're starting with percentages, we automatically write the statement, assume total mass is 100 grams. By doing that, we've now opened the door to allow ourselves to set up the problems where we have 40.0 grams of carbon, 6.71 grams of hydrogen, and 53.3 grams of oxygen. Using each molar mass to convert to moles, we see that our smallest mole number is common to 2 of the elements, which can happen, 3.33 moles. Dividing all our mole numbers by this 3.33 moles, we come up with values of 1, 2, and 1. All whole numbers, so we need not make any corrections, and our empirical formula for this compound would be CH2O. Now, this empirical formula involves carbon, hydrogen, and oxygen, three elements commonly found in organic molecules. And you'll recall earlier in the presentation I mentioned that where we find differences between empirical and molecular formulas, one of those main places is with organic molecules. So what we see here, the 1 to 2 to 1 ratio, may be the empirical formula for several different organic compounds. If we want to determine what the actual ratio is for a given organic compound, we need one more piece of information, and that is the molecular mass of the final compound. And this is something that can be determined experimentally, instrumentally, and combined with the percent composition analysis, we can use those two pieces to come up with the molecular mass, or the molecular formula of the compound rather, and this is what we're going to do in our last example. So to determine the molecular formula, the first thing we need to start with is that formula in its simplest ratio, the empirical formula. If we are not provided with that empirical formula, then we need to go through the steps that we've discussed and calculate it first. Once we have that empirical formula in hand, we then need to use our periodic table and calculate the formula mass for that empirical formula. Once we have calculated that empirical mass, if you will, we need to divide that into the molecular mass. And the molecular mass is a value that will either be experimentally determined or given to us in the problem. When we divide molecular mass by empirical mass, again, this should give us a quotient that should be a whole number. If it does not come out to be a whole number, I would go back and double check your numbers, double check your empirical formula calculation. That quotient then becomes the multiplier for the subscripts in the empirical formula. If you think about it, an empirical formula takes a molecular formula and simplifies it. It's the simplest ratio of elements in a compound. So it stands to reason that whatever the mass of that simplest ratio is altogether should be a whole number fraction, if you will, of what the entire molecular mass is. And that's the premise that we're working under here. So if we consider ascorbic acid, more commonly known as vitamin C, it has a percentage composition of 40.9% carbon, 4.58% hydrogen, and 54.5% oxygen. We're also told that it has a molecular mass of 176.1 atomic mass units. And the question is, what is its molecular formula? Now in this case, we are not given an empirical formula for ascorbic acid, but we are given its percentage composition. So we can calculate that empirical formula by first assuming that the total mass is 100 grams, beginning with the masses of each element. We use their molar masses to convert them into moles. Comparing these mole numbers, we see that 3.41 is the smallest mole number, so we divide all of them by 3.41 moles. And here again we see that we end up with a fraction for hydrogen. We get 1.33 for the quotient. And so 0.33 is equivalent to 1/3. To get rid of that fraction, we should multiply it by 3. But whatever we multiply hydrogen's quotient by, we need to do the same for the other two elements as well. So once we multiply by 3, we get a ratio of 3 to 4 to 3 for carbon, hydrogen, and oxygen, giving us an empirical formula of C3H4O3. And at this point, we take a moment, we pat ourselves on the back, we check our work, say, hey, we did good, we got the whole numbers we expected, but we need to remember that this formula is the empirical formula. It is the simplest ratio of carbon, hydrogen, and oxygen to one another for ascorbic acid. It is not necessarily, though it could be, but it is not necessarily guaranteed to be the molecular formula. We need to go back and use that additional piece of information that was provided, the molecular mass of 176.1 atomic mass units, to determine, is this truly also the molecular formula, or do we need to find the multiplier? So we still have one more step to go. Once we have the empirical formula, this last step really is very, very quick. Finding the empirical formula really is the bulk of the solving process if you have to do it. But once we have the empirical formula, we go to the periodic table, we use the atomic masses to determine the formula mass for this empirical formula, and in this case that comes out to be 88.0 atomic mass units. Once we have that empirical mass, we were given the molecular mass in the problem itself, so we divide the two. And when we divide 176.1 atomic mass units by 88.0 atomic mass units, we find that, rounded off to nearest whole number, it comes out to be 2. And again, obviously here there's going to be a little bit of a decimal trail after the 2, but it should be close enough that you can round it off to a whole number without a lot of rounding taking place. Now this 2 is a multiplier, and we will then take that 2 and multiply it by the subscripts in the empirical formula, and what results will be our molecular formula. So the molecular formula, based on the percentage composition we were given and the molecular mass that we were provided, the molecular formula for ascorbic acid, vitamin C, is C6H8O6.